Today we discuss derivative of inverse function. First theorem, let y is equal to f of x is a differentiable function of x which admits of an inverse function f inverse of y. That means y is equal to f of x is a differentiable function. That is, it is a bijective function. So its inverse exists, then df inverse of y divided by dy is equal to 1 by df by dx, provided that df by dx not equal to 0. Okay, or equivalently we can write it as dx by dy is equal to 1 by dy by dx, provided that dy by dx not equal to 0. Now we prove it, let y is equal to f of x is a differentiable function of x. Since it admits inverse, so we can write x is equal to f inverse of y. Let delta x is a small increment in x and delta y is the corresponding increment in y. Then y plus delta y is equal to f of x plus delta x. That implies and implied by x plus delta x is equal to f inverse of y plus delta y. Now df inverse of y divided by dy, by the definition of a differentiation, limit delta y tends to 0, f inverse of y plus delta y minus f inverse of y divided by delta y. We know f inverse of y plus delta y, x plus delta x, f inverse of y x. So we write limit delta x tends to 0, x plus delta x minus x divided by f of x plus delta x minus f of x. We know delta y is equal to f of x plus delta x minus f of x. If we subtract it, delta x is equal to f inverse of y plus delta y minus f inverse of y. Delta x tends to 0 as delta y tends to 0. If we put here delta y 0, then we have delta x is equal to 0. So we can write it as limit delta x tends to 0, delta x divided by f of x plus delta x minus f of x. Also we write limit delta x tends to 0, 1 by f of x plus delta x minus f of x divided by delta x. If we take a limit on numerator and denominator, we have that is like df inverse of y divided by dy is equal to 1 by limit delta x tends to 0, f of x plus delta x minus f of x divided by delta x. Okay, so that equal to 1 by the rotation we can write df by df by dx. Okay, so we prove the inverse function derivative. We write it df inverse of y divided by dy is equal to 1 by df by dx, provided condition, provided df by dx not equal to 0. Okay, now we discuss an example. If we find dy by example, find dy by dx if x is equal to root over y divided by root over y plus 1. Okay, answer. given x is equal to root over y divided by root over y plus 1. We can write it root over y plus 1 minus 1 divided by root over y plus 1. Then 1 minus 1 by root over y plus 1. Then 1 minus root over y plus 1 whole to the power minus 1. Now differentiate both sides. Differentiate both sides with respect to y. Dx by, we get dx by dy, that equal to d by dy of 1 minus root over y plus 1 whole to the power minus 1. That equal to d by dy of 1 minus d by dy of root over y plus 1 whole to the power minus 1. Okay, that is equal to 0. The derivative of constant is 0 minus here root over y plus 1 to the power minus 1. First of all, it is a function of root over y plus 1. So we write d of root over y plus 1 whole to the power minus 1 divided by d of root over y plus 1 into d of root over y plus 1 divided by dy by chain rule. So we write here that equal to minus x minus y root over y plus 1 to the power minus 1 minus 2 into 1 by 2 root over y, because the derivative of root over y 1 by 2 root y and the derivative of 1 is 0. So we get a 1 by minus of order minus of, so we get a 1 by 2 root over y plus 1 whole square. Okay, now we find the derivative of inverse trigonometric function. Now we find the derivative of inverse trigonometric functions. Derivative of inverse trigonometric functions. Okay, prove that first one, d by dx of sin inverse x is equal to 1 by 1 minus x square root over minus 1 less than x less than 1. That means x belongs to my open interval minus 1 1. Number 2, d by dx of cos inverse x is equal to minus 1 by 1 minus x square minus 1 less than x less than 1. Third, d by dx of sec inverse x is equal to 1 by mod x root over of x square minus 1. Fourth, d by dx of cosec inverse x that equal to minus 1 by mod x root over of x square minus 1. Fifth, d by dx of tan inverse x that equal to 1 by 1 plus x square, x belongs to 1. Similarly, d by dx of cot inverse x that equal to minus 1 by 1 plus x square, x belongs to R. Now we prove these 6 formula. Okay, first we prove this is derivative of a sin inverse x. To prove that d by dx of sin inverse x is equal to 1 by 1 minus x square root. Okay, let y is equal to sin inverse x. If we take on both sides sin y is equal to sin of sin inverse x, that implied by sin y is equal to x. Ix, identity function x, that equal to x. Then we write it in x is equal to sin y. Now we differentiate both sides with respect to y. Differentiate both sides with respect to y. We get dx by dy, that equal to d by dy of sin y, that equal to cos y, So we write dy by dx is equal to 1 by, that implies dy by dx is equal to 1 by cos y. Okay, 1 by cos y, that implies dy by dx is equal to 1 by 1 minus sin square y root over. That implies dy by dx 1 by 1 minus x square root plus minus. Since x is equal to sin y, Okay, here there are two signs, plus and minus. Since by definition of inverse function y belongs to minus pi by 2 open whenever x belongs to minus 1 1 cos y greater than 0. So here we choose only positive sign. So dy by dx is equal to 1 by 1 minus x square root. That implies d by dx of sin inverse x is equal to 1 by 1 minus x square root. Okay. Now we prove cos is derivative of cos inverse x. Okay. Second, to prove that d by dx of cos inverse x is equal to minus 1 by 1 minus x square root. Okay. Look, we know that sin inverse x plus cos inverse x is equal to pi by 2 in inverse trigonometry. That implies cos inverse x is equal to pi by 2 minus sin inverse x. That implies d by dx of cos inverse x is equal to d by dx of pi by 2 minus sin inverse x. Okay. that equal to d by dx of pi by 2 minus d by dx of sin inverse x, that equal to 0, since pi by 2 is a constant, that the derivative of pi by 2 is equal to 0, minus 1 by 1 minus x square root. Okay, that implies d by dx of cos inverse x is equal to minus 1 by 1 minus x square root. Okay, that is the derivative of cos inverse x is minus 1 by 1 minus x square root. Next, to prove that, d by dx of sec inverse x is equal to 1 by root over of x square minus 1. Okay, let y is equal to sec inverse x mod x greater than 1, that is x belongs to minus infinity minus 1 union 1 infinity. Okay, that imply by sec y is equal to sec of sec inverse x. Sec y is equal to x. X is equal to sec y. X is equal to sec y. That differentiate both sides. Differentiate both sides with respect to y. We get dx by dy, that equal to d by dy of a sec y, that equal to sec y into tan y, that is the derivative of a sec. That implies dy by dx is equal to 1 by sec y into tan y, that equal to 1 by sec y plus minus tan y means sec square y minus 1. That the root over is plus minus, so we write here plus minus sec y into the root over of a sec square y minus 1. Since sec y is equal to x, we can write here plus minus x root over of x square minus 1. Okay, the sign before radicals depends on the sign of tan y. The sign before radicals means root over, radicals depends on the sign of tan y. Sign of tan y. Now if x belongs to minus infinity minus 1, then y belongs to pi by 2 pi, then tan y less than 0. That means in the second quadrant pi by 2 pi, that the tan y is negative. Similarly if x belongs to 1 infinity, then y belongs to 0 pi by 2, 0 pi by 2, and then tan y greater than 0. Now we combine these two, we can write, so dy by dx is equal to 1 by minus x root over of x square minus 1 if x less than minus 1, 1 by x root over x square minus 1 if x greater than 1. Okay, combining these two cases, okay, we can write dy by dx is equal to 1 by mod x root over of x square minus 1. That implies d by dx of sec inverse x is equal to 1 by mod x root over of x square minus 1. That is the derivative of sec inverse x. Next, we prove the derivative of cosec inverse x. To prove that d by dx of cosec inverse x is equal to minus 1 by mod x root over of x square minus 1. Okay, prove. We know from inverse trigonometry sec inverse x plus cosec inverse x is equal to pi by 2. Then cosec inverse x is equal to pi by 2 minus sec inverse x. That implies d by dx of cosec inverse x is equal to d by dx of pi by 2 minus sec inverse x. Okay, that equal to d by dx of pi by 2 minus d by dx of sec inverse x. That equal to 0 minus d by dx of sec inverse x. We know the derivative of sec inverse x 1 by mod x root over of x square minus 1. So the derivative of cosec inverse x is equal to minus 1 by mod x square minus 1. This is the derivative of a cosec inverse x. Now we find the derivative of tan inverse x. Okay, to prove that, find d by dx of tan inverse x is equal to 1 by 1 plus x square. Let y is equal to tan inverse x. Tan y is equal to tan of tan inverse x plus tan y is equal to x. X is equal to tan y. Differentiate both sides with respect to y. We get dx by dy d by dy of tan y. That means sec square y. The derivative of tan y, you know, sec square y. Okay, sec square y is equal to 1 plus tan square y. Sec square theta is equal to 1 plus tan square theta. That implies dy by dx is equal to 1 by 1 plus tan square y. That implies dy by dx is equal to 1 by 1 plus x square, since x is equal to tan y. That implies d by dx of y means tan inverse x is equal to 1 by 1 plus x square. Okay, this is the derivative of a tan inverse x. Now we find the derivative of cot inverse x. Cot inverse x. Okay, cot inverse x. 6. Last formula. Let y is equal to cot inverse. We know that tan inverse x plus cot inverse x is equal to pi by 2. That implies cot inverse x is equal to pi by 2 minus tan inverse x. d by dx of, if we differentiate both sides with respect to x, then we write d by dx of cot inverse x is equal to d by dx of pi by 2 minus tan inverse x. Okay, that equal to d by dx of pi by 2 minus d by dx of tan inverse x. That is 0 minus d by dx of tan inverse x, that equal to minus 1 by 1 minus 1 plus x square. That is the derivative of tan inverse x, 1 by 1 plus x square already, minus is there. So d by dx of cot inverse x is equal to minus 1 by 1 plus x square. This is the derivative of a cot inverse x. So you know the derivative of 6 trigonometric function. This is the formula. Now we do exercise 7D. Exercise 7D number 2. Let y is equal to sin inverse 2x. We find the derivative of a sin inverse 2x. We put let y is equal to sin inverse 2x. Then dy by dx. If we differentiate both sides with respect to x, then we write d by dx of sin inverse 2x. Here sin inverse 2x is a function of 2x. Then 2x is a function of x. So we put here chain rule. Then we write d of sin inverse 2x divided by d of 2x into d of 2x divided by dx. Okay. Since the derivative of sin inverse x 1 by 1 minus x square. So we write here derivative of sin inverse 2x with respect to 2x is 1 by 1 minus 2x square into 2. So we write 2 by 1 minus 4x square root over. Okay. Next, number 3, derivative of cot inverse root x. Let y is equal to cot inverse root x. Then dy by dx is equal to dy by dx of cot inverse root x. Here cot inverse root x is the function of root x. Root x is the function of x. So we write d of cot inverse root x divided by d of root x into d of root x divided by dx. So since the derivative of cot inverse x with respect to x minus 1 by x 1 plus x square, so we write here minus 1 by 1 plus root x square into derivative of root x with respect to x, we know 1 by 2 root x. So we write minus 1 by 2 root 2x whole into 1 plus x. Okay. Next we do let y is equal to number 4 cot inverse 2x plus 1. Cot inverse 2x plus 1. Sec inverse 2x plus 1. Sec inverse 2x plus 1. Then dy by dx is equal to sec inverse 2x plus 1, that equal to d of sec inverse 2x plus 1 divided by d of 2x plus 1 into d of 2x plus 1 divided by dx. So we write we know sec inverse x with respect to x 1 by mod x root over of x square minus 1. So we write here 1 by 2x plus 1 mod root over of 2x plus 1 square minus 1 into the derivative of 2x plus 1 is 2. So 2 by 2x plus 1 mod root over of 4x square plus 4x plus 1 minus 1, that equal to 2 by 2x plus 1 root over of 4x square plus 4x. Okay. If we take a 4 from this, we can find the 2 by 2x plus 1 mod root over of x square plus x 1 by cancel 2x plus 1 root over of x square plus x. Okay. These are the examples and exercise of this chapter. Okay. Thank you.